Day of Linux Conference Australia 2013. Yay, well done people. We have got two speakers. We have got Tim Sarong, Florian Haas, and they'll be talking on Ceph object storage, block storage, file system replication, massive scalability, and then some exclamation mark. As a very quick bio, Florian is a Linux high availability and storage specialist. He frequently consults and conducts training on both OpenStack and the Ceph stack. And Tim is currently employed by SUSE as a senior clustering engineer, working on SUSE Linux Enterprise High Availability Extension and the SUSE Cloud product, which is based on OpenStack. He has now got doubts on whether there are there's such a thing as too many log files. With that introduction, can we both give Florian and Tim a warm introduction? Thank you.
Thank you for that. So, for those of you who came in on a kind of tight schedule or kind of late, if you already have those virtual machine images set up, that is perfectly fine and you can follow along. If you choose not to follow along on your own virtual machines, that is perfectly fine too. You will take just as much out of this tutorial and then you are able to retrace your steps later. We actually have made a point to make that easy for you. If you do follow along, please make sure that other than the fact that you have those virtual machines installed and you have run the install sh script, you should make sure that you have virtualization enabled in your system BIOS. So that is a feature that is usually found as Intel VT or AMD SVM. You want to have your KVM module loaded. That is just a modprobe KVM, and it will load the appropriate either KVM Intel or KVM AMD module for you. Obviously, because these use libvirt, you want libvirt-d to be running. And in order to avoid memory hogging, what you really want to turn on is kernel same page merging. That's the fun stuff where you have like multiple processes using a page that has identical content. It's all being merged to one page, and then we just have pointers, and you do that by checking or editing that one file in sysfs/sys/kernel/mmksm run. Some distros ship with that enabled by default, others don't. In that case, you just do an echo 1 into syskernel mmksm run. And by the way, we still have seats, so if you're in the back, feel free to rush in and grab a seat over here.
There's still there's a couple of USB keys going around if you want to copy the virtual machine images onto your laptop. There's one up there and one there and one here, so yeah. Sing out.
So generally speaking, we do have a sort of a theoretical introduction to the Ceph stack, and if you would like, you can keep setting up your machines during that time. However, if you're just starting now, I would actually suggest that perhaps you will leave the following along for later, and then so you don't miss too much of the talk here. Yes, we have a question.
Are we going to be able to download the image later?
So the question was, are we going to be able to download the image later? Now, no, you are able to download the image now, and you can do so just as well later on. So it's on a Linux Australia Mira. I tweeted the info yesterday, and there's also an entry on my blog. So if you go to hostexo.com/blog/Florian, you will find all that information there. And I don't think that the organizer is going to take that off like anytime super soonish. All right? Okay. So we are going to talk about the Ceph stack, and the Ceph stack is a storage stack that provides us with object storage, block storage, file system, a distributed file system, some replication, awesome scalability, and some other goodies. And we are going to walk through those one by one. This is a double slot, so we have a little more time than we usually have in a talk, which is delightful. And this will give us the chance to cover Ceph theoretically in a little more detail than we were able to do in the OpenStack Ceph talk, for those of you who have seen it, and also walk through some interesting practical steps there. Before we get started, you may be wondering just who the heck we are and what we do in this talk. And I will start with my co-speaker, Tim Sarong. That link that you're seeing there is his Google Plus page, so you can find Tim on Google Plus and connect with him there. Tim works for SUSE, and his email address is tsarong@suse.com. Tim's actually based just outside of Hobart. In this talk, or in this tutorial, he will be doing the real work, meaning actually working on systems. The handwriting that you see here is his, and he is also responsible for the cartooning that you will see halfway through the talk. With Tim doing real work, handwriting and cartooning, that leaves me with fake work, hand waving and babbling. So that is my role here. That is my Google Plus page, or at least a short link to the same. And you can find me at florian@hestexo.com. I run Hestexo, which is a professional services company, which is based just outside of Vienna, and that is where I hail from. Okay, so with that out of the way, let's get started with Ceph. So Ceph is really not one thing, but four things. Four relatively distinct things, all rolled into one, and we're going to go through them step by step. Before we do that, well, we're going to give you a quick overview of all of this. So Ceph, fundamentally, at its core, uses object storage. That means that the primary interface to interact with data is not files, is not blocks, is objects. Why? Because in order to build a massively scalable distributed data store, we can actually reduce that to relatively simple operations. What we want to do is we want to be able to write data, read data, perhaps delete some data, but we really don't need to worry about what is our block or sector address. We don't want to worry about what our inode is, or whether we have directories or files or permissions or ECLs or things like that. We don't need any of that to achieve massively distributed and extremely scalable, highly available storage. In Ceph, the basic unit of data is an object, and objects as such are being distributed, replicated, and kept highly available within the distributed cluster. And we're going to look at, in a certain amount of detail, what that means as we get to the practical stuff. Ceph also has a block storage interface, so rather than interacting with Ceph objects directly, we have one abstraction layer that allows us to treat a great number of Ceph objects as one block device, as we would with any other old block device in Linux. So there we have something that appears as a virtual block device, and we can write to it at a certain offset, or read from it at a certain offset, and we can use it for anything else that we can use a block device for. Block storage in Ceph is thin provisioned. It's very space efficient. It supports redirect on write snapshots. It supports cloning and several other interesting things. The third thing that we're going to cover when we're talking about Ceph is RESTful storage. So this is something that, for those of you who are familiar with things like Amazon S3 or OpenStack Swift, this is how we interact with object storage using RESTful interfaces. And that means that we have clients that may be just an HTTP client, and they're using standard web technologies like HTTP, HTTPS, and JSON to retrieve data from the object store, and do so in a very, very efficient and simple way. And then finally, we have a distributed file system, which is the layer that adds all of these things that are interesting to POSIX, and only to POSIX, to the distributed storage stack. So here is where we get a distinction between files and directories. Here is where the namespace actually becomes hierarchical. Here's where we see things like file ownership and permission bits and those things. And as you will see, that is actually a very, very thin client layer that talks to the object store, which makes the whole thing very, very interesting and elegant. Okay, so those are the four things that we're going to talk about, and we're going to look at them both from a theoretical perspective, what's behind it, how does it work, and we're also looking at all of these with a practical view, actually operating on the virtual machines that we have running here, and some of you have running on your laptops as well. So before we actually dive into getting our noses bloody and our hands dirty and our feet wet, or a combination of all three, on those machines, let's take a look a little bit of what is so special about this whole native object storage thing that is at the core of Ceph. So, Ceph is based on a distributed, autonomic, that means self-organizing, and redundant native object store named RADOS. And RADOS stands for Reliable Autonomic Distributed Object Store. So, RADOS is a completely flat namespace. So that means that we don't have anything like a directory hierarchy or anything of that nature. It's completely flat. This is something that is very common to pretty much all object stores. And in RADOS, for each object, we have a name, an identifier. We have a payload or contents, which is pretty much arbitrary in size. And we can also stick onto a RADOS object any number of key value pairs attributes. So we can assign an object attributes at will. We can obviously retrieve them as well, and those are relatively independent of the actual payload. Now, objects in RADOS are assigned to something that we conceptually refer to as placement groups, or PGs. And every PG, every placement group, has a list of object storage devices, or depending on whether you're reading the older or the newer documentation, object storage daemons, where the content of these PGs, so all the objects in a specific placement group, are stored in a redundant fashion. Now, why is this list of OSDs that each PG writes to and reads from ordered? RADOS uses a primary copy mode of replication. So as we're writing an object, it's it, along as would any other object in the same placement group, is first being written to the primary OSD, which is the first entry in this list. And then this primary OSD takes care of where the other replicas go. And how many replicas we have is entirely configurable. So we can and we can change the number of replicas in subdivisions of the object store, which we refer to as pools. By the way, don't be shy. Rather than sitting in the aisles, there's a few seats left over here.
The number of replicas is configurable per object.
So the question was, is the number of replicas configurable per object? No, it is configurable per pool. A pool is an administrative subdivision of the object store, and all of the objects in that pool have a certain number of replicas assigned to them. And the replication to these OSDs is actually synchronous. So we can make sure that when we define we want, for example, 3 replicas of every object in a given pool, as the object is being written, the application, the client that is actually doing the write, does not get an acknowledgement of that write until it has been completed in all of the replicas. Object placement is completely algorithmic. So there is no central lookup database, and there is also no such thing really as a distributed hash table. Now, what is special about that? That concept of data storage is a little abstract, so I tend to like to use it with a bit of a more concrete example. Okay? When we are checking into a hotel, right? That is a data storage problem. I, the traveler, am data, and I wish to be stored in an appropriate location, and preferably such that I actually get my own room and do not intrude on someone else's. So how does this typically work? When we check into a hotel when we're traveling, we typically go to the front desk, and we give our name or reservation number and the duration of our stay or whatever we need in order to uniquely identify the reservation. And then we are assigned a room and we're given one of these key things, right? If your hotel is a little more modern than this one, then it may be a key card, but that doesn't matter. You get something to get to your room, and you get the information where your room is, okay? So in terms of a data lookup, as in I need to figure out where the piece of data am to be stored, what that in fact is essentially a central database lookup. with an optimization, which is they're actually telling me where my room is and I can memorize it, so we've just cached the lookup. Okay? And as with all caches, the cache typically expires, so my reservation is, and the room that I get is only for, I don't know, say 4 days. And if I want to extend my stay, I need to get back to the front desk and do a fresh lookup. And I might then be reassigned to a different room, or the same room may still be available, and it's just being extended, but I still need to go through the front desk. So the lookup, the data lookup of the data storage for me, the traveler, to a room, conventionally the way we do in a hotel is you go to the front desk, they tell you your room, you get a key, and boom, you've just done a central database lookup with caching. Something that we would typically do in a storage solution that operates on the basis of a central metadata service. Now, that works just dandy for a small hotel. So if we have about maybe 20 to 30 rooms, that will be just great. What, however, if we have something like 200 rooms or 300 rooms or maybe even more than that? Well, so what if our hotel is actually fairly large? We could do something that's very, very simple. We could just add more front desks and then hire more people, right? So rather than having one front desk, we might have 3, or we might have 5, or we might have 12 or something. But that really doesn't work too well, because what that does is we can now handle more lookups in parallel. So if we have a larger group of travelers, so we can always handle 3 at a time. What it doesn't solve is the problem of actual data assignment, because what might happen is Tim and I both coincidentally travel and stay in the same hotel, and we both approach the front desk, and I'm being told my room is number 365, and then Tim, strangely, is also being told his room is 365, and then eventually what's going to happen is one of these transactions is inevitably going to fail, right? So either the system is smart enough to detect the conflict and then kick it back, or we just meet at what is ostensibly our door, and we both say, well, we actually don't think our relationship is quite ready for this yet. So, so one of us returns to the front desk and say, oh, what the hell's up with you? Please give me a room that is not occupied yet, right? So that is the classic lock contention problem that we have in these database lookups, right? If we allow like multiple clients to access the same database, the same central database at the same time, we might work relatively well normally, but if there's any conflict, then one of the transactions has to be kicked back, and that doesn't scale really well, because the larger the onslaught of travelers becomes, the greater is the probability that we're going to get one of these conflicts and then we're going to have to roll it back. So not really too good for when we actually want to grow our hotel. We could do something different, however. We could build several completely identical buildings. Okay? Now here's where a little bit of magic comes in. The buildings are so identical that one room in the one building has the exact same view as the same room in the next building, and then next building, next building. So a little bit of magic there. And we can assign guests on a pseudo-random basis, such as, for example, say, second letter of their first name. Okay? So for me, that would be L, and for Tim, that would be I. So we could have, like, several of these hotels right next to each other, right? And one of them, and let's say we have 26 of them, and then one says A, one says B, one says C, and then the assignment is based on the second letter of their first names. So now we have sort of partitioned the problem a little bit, because now we don't have to access the same front desk. We can, the lookup database can be just for those individual pieces, and then Tim goes to one building and I go to a different building, and we might actually be assigned the same room in that building, but now we no longer collide because the space is actually partitioned, right? So big hotel there, or many, many, many hotels. And that is exactly the approach that we typically refer to as a distributed partition hash table. That's exactly how that works. So we're sub-partitioning the namespace, essentially sort of from the get-go, and then we do our assignment within those, okay? Now that's actually pretty good approach for when we want to grow from, say, one order of magnitude to the next order of magnitude, and then perhaps one more, okay? But what if our hotel was not small, was not large, was not big, was not huge, but was absolutely gigantic? Okay? Hotel, for example, with 1 billion rooms. Okay? So let's assume we want to build and organize a hotel with 1 billion rooms, which is relatively similar to the challenge of managing, storage at a petabyte or exabyte scale compared to, puny gigabytes and terabytes like we commonly do today. So this creates some interesting challenges. The hotel with 1 billion rooms, and I've been told I should use the term the hotel at the end of the universe for this, creates some really interesting challenges. So for example, the whole thing with the room number doesn't really work so well anymore. Okay? Because if I have a room number like that, I might know how to get to the 156th floor of the hotel, but to get to the 398,481st room on that floor may be quite a walk. And besides, it doesn't really help for me to sort of memorize that number because it becomes essentially pretty meaningless. So that's one thing that doesn't really work so well. So this whole lookup thing, not so cool. We're also having a bit of a statistical problem with a hotel with 1 billion rooms. Because in a hotel with 1 billion rooms, it's relatively likely that at any given time, about 10,000 rooms are probably going to be on fire. Give or take. Right? Maybe 20,000, maybe 30, we don't know, but a substantial number. And there will probably be about 120,000, 200, 300,000 rooms that are currently under some sort of maintenance because they had a water leak or they have the walls repainted or something. Or we might just build them or we might tear down the building, right? Something like that. All of that is actually relatively probable to occur at some place in the hotel. So that doesn't work too well. Because we have to remember that at a certain scale, something is always going to fail. Fact. Period. End of story. If it's highly unlikely that everything is going to fail at the same time, which means basically the hotel with 1 billion rooms with maybe 100,000 buildings is all going to get knocked out by the same alien spaceship or something. But then we have other problems than assigning our travelers, probably. But it is perfectly safe to assume that at a certain scale, something is always going to fail. And we have to build and engineer the system for this. So, what is it that we really need in order to manage our hotel with 1 billion rooms? In other words, what is it that we really need in order to manage like really, really, really big distributed replicated data storage? Okay. So, because we've already established a thing with the room numbers to identify the room is pretty meaningless, we should really use something that we already know about ourselves to identify where we need to go. So for example, that might be a fingerprint or an iris scan or something of that nature. And then we use this to identify ourselves. So when I get to the hotel, I put my finger in a fingerprint reader and I know exactly where I need to go. I know where my room is, something. All of that has to be done by the system by itself. What I essentially want to do is I want to go somewhere where I have something completely automated that takes this information and automatically guides me to my room. So I no longer need to care where it is because it could be anywhere, right? So what I want really is one of these neat little automated robotic helicopters that read my thumbprint, and then I get in, and it airlifts me to my room. That's what I want to do. Because the airlift thing is just kind of nice because, as we already established, we have this bit of a walking problem on the 156th floor, right? So airlifts would be really nice, and then make that completely automated, I'll put in my thumbprint, and there we go. So now we have sort of solved the allocation problem. Right? We have something that takes something that we already know about ourselves and automatically gets us to where we want to go. That is not all of the problem that we need to solve. So for example, we also need such that we can still enter our room when housekeeping comes in and does our room. We want some robots that automatically move all our stuff when we can't enter a room. So if there's housekeeping in there or maintenance or something, we want something like this to move all our stuff completely automated to a completely different room, right? Including the umbrella and the bag and the kid's teddy bear and the pillow and whatnot. And we want all of this to automatically move to a different room because the system doesn't really care where my room is. I don't care where my room is. We already established that the rooms are magic because they're all completely identical and they have the same view, etc., etc. So I don't need to care where my room is. And if there's housekeeping or maintenance or the walls are being repainted, I don't really want to know about it. Instead, I just want to be taken somewhere else by this magic thumbprint reader helicopter system. And then I need something that has actually gotten my stuff there before I arrived. So I need one of these fancy little fast robots. That solves the maintenance and housekeeping problem. However, fires are typically not scheduled. So the fire problem is one that we still need to cover. So what can we do to combat that is we need some magic replicators that duplicate all our things that are in the room and store them safely somewhere completely different as soon as we put them there. Because I don't want to lose my stuff in a fire. So we want something like this. Okay? Fancy little cameras and things that scan all of our stuff, right? And then all of that is connected to a MakerBot or something that duplicates everything for us. And that would include, you know, my water bottle and my phone and my laptop and my cache. Useful.
I'll put that in the next version.
Yeah. And my dog, whatever. And so all of that automatically goes to a different room, like as soon as I put my stuff into the room. So ideally what I would want is, as I enter my room and I close the door, I want to experience just a little bit of pushback, just a little bit of additional latency, because that's what it takes, that's all the time that it takes to scan everything and replicate everything, and then load it on one of these fancy little track robots and move stuff elsewhere. So that would be cool. So in summary, what do we need? Something that takes a piece of information that we already know about ourselves, which automatically moves us to a room as soon as we read this piece of information. Something that automatically moves our stuff from A to B when my room is not available. And we need something that automatically replicates all my stuff when I first get in there so I don't lose my stuff in a fire. Right? So far, so good. The nice thing about it is, as far as data storage is concerned, Ceph actually does all of that for us, which is really kind of neat. So with Ceph, I can actually manage in a meaningful and useful way such that I can actually use it as a regular user. The billion-room hotel, or in data terms, the petabyte or exabyte storage, which is really kind of cool. And now we're going to look at how that is actually done. Ceph implements an algorithm called CRUSH, Controlled Replication Under Scalable Hashing. And the interesting thing about CRUSH is that this algorithm is known to pretty much everything that plays with the Ceph cluster. That is the components of the cluster itself, but also all of the Ceph clients are aware of this algorithm. And because this algorithm is generally available to everyone and everything in the cluster, the only thing that we actually need to distribute in the cluster are the parameters to this algorithm. And in Ceph speak, we call that a crush map. So the crush map is the stuff that is actually distributed across the cluster, very, very small bits and pieces of information. That is all that we need to pass around, and that's basically gossiped across the cluster. And if we have hundreds of nodes, if we have, it doesn't matter. If we have less than 10 nodes, tens of nodes, hundreds of nodes, it all works the same way. And we don't have any sort of central lookup instance, which, because of the aforementioned locking issues, would completely kill performance at scale. Now, we already mentioned OSDs, object storage daemons. And what's cool about OSDs is that all OSDs, just like everything else in the cluster, know about the current map, the current crush map that describes object placement. And they can also propagate that if they are sort of endowed with the ability to do so. And They get that authority from what we call monitor servers, or MONs, and they act as arbitrators to the cluster status and as authorities for the placement map. If you want a little more detail about how monitor servers interact with OSDs and how they dish out their leases and how they delegate their authority, please go read Sage's 2006 and 2007 papers on Ceph. I don't necessarily want to treat you to his full thesis because that might be a little bit long. But the two papers from 2006 and 2007 are really easy to read and explain this very succinctly, where it's one of those technical reading experiences where you go, hey, yeah, that's totally logical. That's the way that you need to do that. And it's not so much clever as it is really smart. Because as we all know, cleverness is the enemy of stability. The MONs themselves use a distributed consensus protocol. It's also known as a part-time parliament protocol. I understand you are just in the middle of an election campaign, so you may be familiar with a part-time parliament.
This stuff's more fun than our election campaign, though.
Does this also last 8 months?
Well, has anyone been arrested over Paxos yet?
Not that I'm aware of.
See? The MONs use a distributed consensus protocol and algorithm which is based on Paxos. Paxos is a distributed consensus algorithm that I think was first described in about 1995 or 1996. Ceph is not the only distributed technology that uses Paxos in some way, shape, or form. So for example, if you are familiar with the Pacemaker high availability stack, there is an add-on to that called Booth, which is built for site-to-site clusters. Or multi-site clusters, and they define or arrive at consensus using Paxos. For those of you that are familiar with Zookeeper, not the conference management software for LCA, but the other Zookeeper, that uses an algorithm based on Paxos. So that is actually something that is fairly common, reasonably well understood in the literature, and is in relatively wide use. Was there a question? Okay, so really, if you want to read up on those papers, they're really cool. Now, what's interesting is that both MONs and OSDs operate entirely in user space, as do all of the Ceph daemons, really. This is a departure from stuff that we've seen in other distributed storage technologies, like, for example, the Lustre file system. Lustre does a lot of its work in kernel, both client and server side. Everything that happens in Ceph server side is entirely in user land, and there's only a few relatively thin client layers that are implemented in kernel for the file system and for RBD, as we're going to get to in a few moments. So let's take a look. So we have a total of 4 virtual machines that you can connect to. They're named Alice, Daisy, Eric, and Frank. If you looked into your Etsy host file, there also at some point was a Bob and Charlie in this demo, but we try to not overtax our laptops too much. The way to connect to these is shown at the bottom. I hope that is legible. So you connect to these boxes with Secure Shell as root to 192, 168, 122, and then 111 is Alice, 114 is Daisy, 115 is Eric, and 116 is Frank. The password, the root password for these is Hastexo, H-A-S-T-E-X-O, all lowercase, and please feel free to put your SSH pub key into the .root/authorized keys file. By the way, if you choose, you shouldn't, but if you choose to take these virtual machines with you and plug them into a network that you own on and somewhat internet-facing platform, be aware that there's my public key in there for root and Tim's and potentially your own. So if you actually want to put this out on the internet, prepare for a visit from Tim and me. No, so seriously, if you want to deploy these boxes, that's perfectly fine, but make sure that you actually clean out your root authorized keys before you do so.
Init scripts that ring you guys when they get booted?
What was that?
Do they have any init scripts that ring you guys when they get booted?
So the question was, are there any init scripts or backdoors or things that when they get booted? Nah.
We didn't have
And
time.
if we did, we wouldn't tell you, quite frankly. Okay.
I was just wondering how many people are having trouble getting it going. I mean, I've got this up going and I've made a few changes. I'm happy to go around through it.
Yeah. So the question was how many people have trouble getting this stuff going. So they should work unmodified if you're running Ubuntu. They should work unmodified.
Changes.
What was that?
Fedora needed some changes.
Fedora might have needed some changes.
Debian stable.
Debian stable. Does that work?
I need to make changes too.
Okay,
Yeah, I
so
can make a couple
there's
changes
no
also.
guarantee that you don't need to make any changes to these. I can tell you I created them on Ubuntu 12.10 and they should work on unmodified there. If they're not, hey, it's LCA. You get to hack. Huh? No, so we're aware of two things that you need to change in OpenSUSE. That is, you need to change the emulator line from userbin KVM to userbin QEMU KVM.
Same for Fedora.
And same for Fedora? Okay, so in Fedora, the same emulator is userbin QEMU KVM. And then on OpenSUSE, rather stupidly, you have to change the machine type from PC whatever it is to just PC.
Yeah, I
Okay.
changed mine to PC 1.0 rather than 1.2, and that seems to
Yeah, but the thing is, so comment was set it to PC 1.1 or whatever, but the problem with OpenSUSE is actually it wants PC 0.12 or whatever. And then if you just use PC, that's fine, yeah.
That actually
Okay.
defaults back to the most recent one by magic.
Yeah, yeah, actually by green magic in that case. Okay, so like I said, you know, if you can get your stuff going, great. If you can't, just don't worry about it for now because you will take more out of this tutorial if you just watch, rather than if you're trying to now scramble and get things done and then try to catch up. So the first thing that we're going to show you is we have a running Ceph cluster on these boxes, and we can use a utility which is creatively named Ceph to check the status of the current status of the cluster. So we do Ceph dash lowercase w, and that should give us a current status of the cluster. This may sound well, or look like something like Sumerian to you at first sight. But you actually learn to parse it relatively quickly. The most important thing is that we see at the very top is a general overview or general, we can get a general idea of the overall health of the cluster. Generally speaking, if it says health okay, then health of the cluster is okay. There might be a health warn or health critical or other things. And then in the next line, we get our current mon map. So that is the current monitor service that we have in the cluster. What we did in the configuration for these is we put, let me break that here real quick. Can you just control C that? Just so it doesn't roll over. Thank you. What we have here is 3 mons. All of the 3 Ceph cluster nodes are also monitor servers. And that is something that you do for mon high availability. So what you can do is you can have a single mon. If you lose that, you're kind of screwed. Because the mons is how clients actually connect to the cluster. And that's the only piece of information that we need from the client to connect to the cluster. Once it has a mon, a single mon that it talks to, it finds out about all the other mons in the cluster, where all the OSDs are, etc., etc. But if you have one and you lose that, you're kind of in trouble. If you have 2, that's actually a really bad idea because it uses a consensus algorithm based on quorum. And if you have just 2 nodes or 2 mons in the cluster, you lose one, the other automatically loses quorum and is also unavailable. So minimum number of mons that you want to have in a Ceph cluster in order to be highly available, 3. And generally speaking, you would use an odd number. Okay, we have an OSD map. So we know about the OSDs in the cluster, object storage daemons, and currently we have 3 OSDs up and also 3 OSDs in. So up means that the OSD daemon is actually running and is responding on the network. And in means the OSD is currently eligible and available for data placement or data storage. And we're going to see what happens if we do things with these. And then we get a little bit of information about our current placement groups. So we currently have 840 placement groups in the cluster. They are considered active and clean, so that is to say we have no degradation of storage here anywhere, everything is wonderful. And something that I've failed to mention up to this point, we also have in this cluster are 2 MDSs, metadata servers. Those are only relevant to the Ceph file system, which we're going to get to at the end of the tutorial. So for the time being, please bear with us, and we will get to that as we go along. So that is the current status of the cluster. What got us here? Ceph has a single central configuration file, just a second, and that is etc ceph.conf. Yes, we have a question.
Yeah, but related to Ceph-W, where you had E1, for example, after the map is set.
So the question was, what do the various E's mean in the in the output of Ceph-W? So the E1, E155, E66, and so forth. It's an epoch. So all of these maps in the cluster are versioned, and those are just the version numbers that increase. And it's actually really, really cool how it's done that no OSD and no component in the cluster ever sees any of these version numbers go backwards. It's like really slick. That again is one of the things that you will totally geek out about in the papers when you read them. Okay, so the next thing is what got us here. We have a single central configuration file /etc/ceph/ceph.conf. There you go. And this is actually relatively simple and straightforward. There's nothing super duper fancy in here. Ceph uses an authentication service called CephX, which we can use for both clients to authenticate to the cluster and individual cluster daemons to authenticate to each other. It's essentially based on identities that are stored in the cluster, and those are pretty much using shared secrets. We can define a specific log file if we want to. In this case, we're just logging everything to var log ceph and then cluster ID, cluster name and daemon ID. By default, the cluster name is Ceph, and the daemon ID is all the stuff that we have like after the dot of the various daemons. We have defined 3 different mons on our hosts named Daisy, Eric, and Frank. By default, these listen on the monitor address or monitor port 6789. And like I said, you want to have at least 3 of these monitors in any Ceph cluster that you wish to be highly available. And Ceph cluster that you wish to be highly available is like river that you wish to be wet or something. So that should be a given. If we scroll down in this config file, we have a few MDSs. There's really not that much that we need to configure about them, but we'll get to MDSs a little later on. And then we have the OSDs. So the OSDs are actually the data storage workhorses in the cluster. And of these, we might well have hundreds. It is a relatively standard design practice to have 1 OSD per physical storage disk that you have in the server or in the individual node. And it is relatively common for a Ceph storage server to have between about 4 and 12 spinners in it. So if you're thinking that, oh, I'm gonna procure hardware for a Ceph cluster that would also work really, really well for the dinosaur technologies of days of yore, with typically 48 disks in them and whatnot. That is not your ideal Ceph cluster or OSD box, really. OSDs are really, really smart in what they're doing, so they do consume a fairly significant amount of processing power and memory. And what you typically want to shoot for is you want to plan your OSD such that you have at least about 500 megs of memory for every OSD in there. And and for other reasons as well, and that is OSDs use journal writes. So all the writes that happen to an OSD go into a journal, and either then, that is subsequently, or in parallel to the file store. And what you typically do is you have a number of spinners in the box, and then you have one or two really high performance, high bandwidth SSDs in them, such that you use the SSDs for journal devices, you partition them up, and you use them for journal devices of your OSDs, and then the actual file stores are on the spinners. And from that, it follows relatively logically that you have a box with 48 disks, 48 spinners, and just one SSD hosting all of the journals. That SSD is just going to be too slow. Okay? Yeah, we have a question in the back.
Just wondering about dense Ceph deployments, what's your sort of space limit in the data center?
Are you talking about storage space limit? Okay, so the question was, what is the storage space limit of a Ceph cluster in a data center?
Sorry, power and cooling constraints, right? You have limited number of floor tiles, and therefore you think you'd like to make it dense.
Ah, okay.
Lots of disks.
Yeah. Well, you can do that. But then in that case, what you would typically do is you would completely forego the SSD approach and actually put your journal on the devices, because then you can parallelize that to a certain extent as well. Yes?
Would you prefer to build RAID systems first and then put
Yeah.
solid, or vice versa?
So question is, do we need RAID for Ceph? Nope.
Need, but would you
Yeah,
prefer it?
no. I also would not prefer it. No. Ceph does takes care of its own replication by itself. So no, you don't build RAID on for
So
Ceph.
instead of building a RAID, you would just use all single disks as a single one.
So the question was, instead of building one RAID with multiple disks in them, would I use them all separately? Yes, you essentially use them as a JBOD, and you're deploying one OSD per spinning disk. Roger?
So if you run multiple SSDs, you can presumably increase the density of the disks per host?
If you run multiple SSDs, can you increase the density? Yes, you can. You can, of course, run a whole Ceph cluster with like several petabytes in all SSDs, if you choose to. That will typically be limited by budget constraints. So the nice thing that you can do with a Ceph cluster is you can build something that is really awesomely distributed and very, very fast for using, say, 7.2K RPM SATA spinners with 2 terabytes each, which are really cheap disks, and you just invest a few bucks extra into the SSD. So we have a question, Red Hat person over here? Yes?
Yes, you mentioned that typical configuration would have 4 to 12 spinners per box. As we change this number to a lower number or higher number, what do we achieve? Does it change from IOPS focused to throughput focused, or is it something else?
So the question was, I said that the standard number is about 4 to 12 disks, and what changes or what change can we expect if we're using more or less of this?
Yeah.
You just happen to hit different performance limits, right? So if you're using, it will still be fine in terms of performance and utilization and whatnot. But for example, this is a standard thing that we come across relatively often when we do projects like this, is someone buying a server with lots and lots and lots of spinners and 1 or 2 SSDs, and then what happens is what I said earlier, it's actually the SSD that becomes the performance bottleneck. So in that case, you can still use the box, and what you would do is you would instead just put the journal actually on the file store, on the spinners themselves, but you may just have wasted a little bit of cash for a few SSDs. Bruno, you had a question?
Yep. All the Ceph deals with disks of different size and performance? Because over
Yeah.
time,
So how does Ceph deal with the heterogeneous type of disks and arrays and things? In the crush map, you can define weights. So you can say give preference to this type of disks, or this box has this much more storage than the other box, etc. So it deals with that. It deals with it in a way that is not completely self-adjusting, I think is fair to say. Oh, what happened here?
what happened in one of the other rooms?
Yeah. No, I mean, it's fine for me, but for those following along, that might be a bit problematic. Oh, here?
Just having a look here. Lights. Come on. Okay, let's go back to
Room? Full? Dim? What?
full.
Better? Wonderful. Okay. All right. Okay, more questions? Yes?
Sorry, just to go on the RAID question. I understand that Ceph is looking after the resilience of the system, but would it not increase the speed to have a RAID as well?
So question was, would a RAID not increase the speed of the system? No, it would not, because the nice thing about Ceph is that all of the writes that are, or all of the I/O that's coming into the system is actually being distributed across the whole cluster. So the classic issue that you typically have in standard issue storage solution, which is you typically get periods of relatively high locality of I/O, is just not happening. Instead, you're hitting in a sufficiently scaled out cluster. You're just hitting sufficiently many nodes that you're distributing the load nicely. So you're actually not getting that kind of locality. It's very uncommon for a sufficiently distributed Ceph cluster to be hit with writes to a single OSD of more than about 4 to 5 gigabytes at a time. Okay. We'll take one more, and I'll have to ask you to pull back a little bit because we need to sort of get going. Yes?
Coming back to SSDs, what would be a good baseline SSD to spinner ratio?
What would be a good baseline SSD to spinner ratio? A good rule of thumb would be, for example, if you're going with... a good rule of thumb is generally about 4 OSD journals per SSD. Okay. Give or take a little bit. So if you have, say, 8 spinners, 2 SSDs would be perfect.
Okay. Thank you.
All right. So we're going to skip the whole Rados Gateway stuff because we're going to get to that in a second. What we're going to do instead is we're going to show you real quick what a Ceph OSD actually looks like. Here be dragons. Be very afraid. Can we just see a mount real quick? So what we have here is we have a separate file system for the OSD because it's on a separate disk. In that case, it is the XFS file system that is mounted from dev VDB1 to varlib Ceph OSD Ceph 0. Okay, and we have 2 theoretically recommended file systems for Ceph OSDs. In practice, I would actually recommend only one. Those 2 that are theoretically recommended are ButterFS and XFS. ButterFS sort of being the perfect option when it's ready. People have been saying nasty things about ButterFS like it is 2 years from production and always will be. I will not go that far, but for right now, arguably, it's still marked as experimental. You probably don't want to entrust your petabytes and exabytes of data to ButterFS. Ceph OSDs actually do a few clever things with ButterFS, such as, for example, when using ButterFS, you can do the journal write and the file store write in parallel, which can greatly speed up the process, because what you can do if the journal write fails, you just roll back to the previous ButterFS snapshot, which is kind of cool. So you have a consistent state again. And there's various other neat little things that it does with ButterFS. For right now, my general recommendation in Ceph projects is to use XFS, which is really fine and helpful as far as that is concerned. There is support for ext3, ext4. It has some performance issues because of the way those handle user extended attributes. But generally speaking, XFS should be a very safe bet. If we actually look into this directory and do an ls, or even, well, actually go into current in here. There we go. And do an lslr in here. Yeah. It looks so much like a normal regular file system, right? So this is very much optimized for Ceph's own purposes, for object storage, and it is one of the things that sort of tend to scare people the most about Ceph, which is that if you're running into a problem where essentially all of your mons, all of your monitor servers are completely unavailable, you can't connect to either of them, it's really, really hard to get your data out. That is something that where people usually get more of a warm fuzzy feeling when they're using GlusterFS, because in GlusterFS all of that is very transparent. If I put data into a GlusterFS, then I can look into the brick, the underlying local file system that Gluster exports, and in there is exactly the same file name, and if I'm not using striping, the same file size and the same attributes, etc., and I can easily get my data out of GlusterFS even if I've killed my GlusterFS. But for Ceph, that is not so much the case. So, and you also really, really, really don't want to muck around manually in these things. You don't want to VI one of the files in here. Don't do that. Not cool. So, well, of course. So you can do it, and you get to keep all the pieces. They're all yours. Yeah. Yeah. Okay. And then on the other hosts, if we just move over to Eric here real quick, that's our OSD1. So that looks pretty much exactly identical. Could you just switch to Eric real quick and look into the OSD there? So same thing. So that is Ceph OSD Ceph1, and yeah, there we go. And then it's the same, right? Okay. So that is our running Ceph cluster, and you can imagine that Frank looks roughly the same. That is our running Ceph cluster, and we can interact with this Rados object store, not with VI in the OSDs, okay, but with a number of client-side APIs and tools. And that's what we're going to look at next. And here's another thing where you can follow along. This is on Alice. So Alice is our client node for everything, but most of the stuff that we're running on Alice, you could also run on all of the other hosts, okay? And in the /root on Alice, you will find in total 4 directories, and they're named 01 Rados, 02 RBD, 03 Rados Gateway, and 04 CephFS. And that's exactly the order in which we're going to do them. So we're going to start with Rados. And the first thing that we can do is we can just get a list of the Rados pools in here. And just so we don't, waste a lot of, get a lot of friction and things by us reading out or spelling out commands, we've decided to just put everything in neat little shell scripts that you can then review and see what they're doing under the covers, and all of these are running with set-ex, so you can actually see the commands as they're happening. So the first thing that we're doing is we're just getting a list of all the pools that we have in the Ceph cluster. And 3 of those are always available by default, and those are named data, metadata, and RBD. The data and metadata pools are for the Ceph file system, and RBD are for Rados block devices. And the others are all because we have created a Rados gateway in here for you already. And there's one that we're using for testing purposes, and because we're tremendously creative, we've named it test. So the first thing that we can do here is we can just create an object and put that into this pool. Okay, so what we're doing here is there's a command line utility named Rados. Again, very creative. We're defining what's the pool that we want to interact with. That's the -p option, test. We define what is the client identity that we want to use, and in this case it's the one that Ceph creates when we first install a cluster, called client.admin. And we define a key ring that we use to identify as that identity to the cluster. So in this case, Rados-p test in client.admin, Ceph key ring. By the way, we could leave all of that out except the p test, because they're actually the defaults. Okay, so by default, you're connecting to the cluster with the admin identity using Etsy Ceph keyring as a default keyring location. And then you put an object in there. Rados put. Object name, and then what gets cut off at the end of the screen here is the actual content that we want to toss in there. So what we're doing is we're echoing hello world into this binary, and that gets piped in on standard in. And then we have created a Ceph object named hello in the test pool. And we can retrieve that again with, that's the get object thingy. There we go. Again, Rados, blah, 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 some options, get object name, and it just spits out the content of this object from on the command line. Okay, there's a few other things that we can do with objects. As we mentioned before, objects don't only have a name and some content, but they also can have extended attributes. That's the next thing. So on this object, there are 2 attributes. Foo with the value of bar, and spam with the logical value of eggs. And you can do that with as many attributes as you want. So you can define new attributes, you can set them, you can retrieve their value, you can update them, etc., etc. And then finally, there is not only the possibility to get and retrieve the object, but we can actually find out where a specific object is. Okay? And that is what we do with this test map object thing. This is actually a 2-step process. We've rolled it into one script. You retrieve what is called the OSD map, which is essentially information of where all of the OSDs are. And then we use this OSD map tool utility to figure out, okay, where is the object named hello? And then it tells us, okay, it's part of that placement group, and it is currently assigned to the OSDs 2 and 1, which happen to be the OSDs on Frank and Eric. Okay, so in the background, while you're not watching, Tim is now going to do something nasty, which is kill the OSD on, say, Eric, while I click in here and do my Ceph-W. There we go. So currently, as you can see, 3 OSDs, 3 up, 3 in. Everything wonderful, everything dandy. And then after some time, we're going to see that one of those OSDs are going to be down. Have you killed it yet? There we go. 3 OSDs, 3 OSDs, 3 OSDs. Wait for a moment. Which one did you kill? Eric or Frank?
Eric.
Eric. Okay.
Eric should be dead. I kicked him out too.
Yeah, okay. There we go. Right, 3 OSDs, 2 in la la la, so let's do that again. Ta-da. As you can see, 3 OSDs, 2 up, 2 in. Oh, you actually kicked it out?
Yeah.
Ah, okay.
Sorry.
That was too quick. So we have these 2 statuses. So one is up and down. That just means, is this thing actually alive and is it responding on the network? And we have in or out, which means, is it available for actual data storage? And what Tim did, he kind of normally an OSD goes to the down to the down status, and then it waits for about 5 minutes, and then it's actually out. And then what happens is this thing that we call backfill and recovery. So what we can do now is, lo and behold, this has been completely reassigned, right? So prior it was 2 and 1, and now we killed 1, and now it's 2 and 0. Isn't that wonderful? So what Ceph does is, not only does it keep our data available as nodes become unavailable, but it actually restores a degree of redundancy to what we have configured completely automatically. Huh? So it deals pretty well with the room on fire problem. Okay, and we can fire that back up while I go along. Oops. Wrong direction. Okay, and then there are several high-level client layers that Rados ships with, and that's what we're going to concern ourselves with in the last just over 30 minutes of this tutorial. So one of those high-level client layers is Rados Block Device, or RBD. So RBD is a thin provision block device that stripes data across multiple RADOS objects. So we have a block interface. Everything that we write to this thing actually gets striped across multiple RADOS objects in the cluster. And then all of the distribution and replication, HA and whatnot, all of that happens at the RADOS level. RBD doesn't have to care about this, which makes it a very, very thin client layer on top of RADOS, compared to having to do everything in regards to replication and HA. RBD supports read-only snapshots. These snapshots are redirect on write, and they're super cheap. Because everything is thin provision, we can use much the same facilities in order to provide snapshots, and that's really, really cool. It supports cloning. Cloning means that we can designate a snapshot as a master copy of other than writable RBD images, which is cool. And with that, it of course becomes very suitable for maintaining things like template-based virtual machines, which is why RBD is heavily used in cloud technologies like OpenStack and CloudStack and others, because it's just very, very useful for this purpose. Now, it actually comes in two flavors, not one. We have RBD, which is a kernel-level block device driver. That made it into upstream Linux in 2637. If I use an RBD that way, I just map it, call it mapping, and then it becomes a virtual block device that pops up on my Linux box. It's dev RBD something, and then I can use it just like any other old block device. What we can also do is we can integrate it directly with virtualization solutions. So there is QEMU RBD, which is a user space storage driver for both QEMU and KVM, and that is built on the librados C API. So with that, we can avoid the kernel round trip that we have to go through if we're mapping a block device for use cases where it's simply not needed. So this means QEMU itself becomes an RBD client, connects to an RBD image, and then presents that as a virtual block device to the guest. So let's take a look at this again. And now here is where the tutorial is a little tighter than it was going to be, because we uncovered a couple of interesting RBD bugs just yesterday, which Sage was nice enough to fix, but we just haven't had gotten updated packages yet. But oh well. So next chapter, O2 RBD. There we go. And again, we have a simple script there which we can use to just create an RBD. There we go. Very simple. We do RBD, and then this is kind of nice. Pretty much all of the, well, not quite all of them, but pretty much all of the client user space management utilities in RADOS support identical command line options. So the -n for selecting the client identity is always identical. The -k for selecting the keyring is always identical. So the same thing is true for RBD. What we're doing here is we're creating an RBD image with a size of 512 megabytes named test, and then doing an ls of the same thing to just show that it is in fact there. The block device as such is thin provisioned, which means that the space that we're defining here is not taken up immediately. That is only the maximum space that it can eventually take up. So for example, if I use the RADOS utility to list the RBD pool, so I'm using sort of a lower level utility now to look under RBD's covers, what I can see here is that there's actually just two RADOS objects that have been created in this, namely the RBD directory, which has information about all of the RBD images in the pool, and a header object, test RBD, and that's it. Only as I write to this device do we actually get additional objects that are being allocated. Yes?
Does thin provisioning have a performance impact?
Does thin provisioning have a performance impact? No. Okay, and we can then map this thing. This is what we do with the O2 map SH. So here again, we use the RBD command. In this case, we actually have to matprobe the RBD module. And once we do that, it becomes available as a block device. Dev RBD 0, and under dev RBD, here we go. We also have some UDEV managed, reasonably named symlinks in there. Okay, so rather than you having to remember the device number RBD0, it is the device in the RBD pool or the image in the RBD pool named test. So it's dev RBD test that you can use here. And if we're fancy, we can now, for example, go ahead and make a file system on this thing. So for example, that would be mkfs-t xfs, or yeah, like that. And then you just do dev RBD test, and it should hopefully happily create a file system for us. And the terminal is really slow, but that's okay. So we can use this as with any other block device. The next step in the demo would have been a fancy snapshot, but that's where the bug hit us. Yes, we have a question.
Just quickly, can you present the block device to multiple?
Can I do what?
Can you present the block device to multiple machines so you can use a cluster file system on it?
Can I present the block device to multiple machines? Yes, I can. In fact, it is a bit over permissive in that regard, such that there is actually no locking mechanism akin to, well, hang on, built into RBD. If you're putting a lock manager for an OCFS2 file system or GFS, you can perfectly do that. What it doesn't do is something like SCSI SPC's 3 persistent reservations. Such a thing does not exist. And the question is, will it ever? Because it happens to be distributed, whereas all of the SCSI stuff is pretty much centralized. Okay? So yes, but you can definitely absolutely map it from as many clients as you want, but you do need to take care of coordinating access to the block device. Again, if you fail to do so, you get to keep all the pieces.
So there is a locking tool that lets you do cooperative locking, but it isn't enforced for you. Okay.
So to get that on the video, there is a locking tool that does cooperative locking, but that really doesn't get enforced. Okay, which SCSI 3 PRs do, unless you preempt them. You actually have to say, I'm wielding the big stick now and I'm beating you to a pulp.
So is there any locking in the QEMU? So you could actually start a VM on 2 different machines? Ouch.
So locking in the QEMU layer, no. But what is in the QEMU layer, which is actually really cool, is the caching is live migration safe. So this is a problem in QCOW. If you're running off QEMU KVM off of QCOW, then you have to disable caching if you want to be able to live migrate that virtual machine, because it does fancy stuff that is totally not cool during the migration process, and that is not true for the RBD storage driver. So you can actually use RBD caching defined as, in your libvirt config file, you're saying disk such and such cache equals write back, write through, whatever, and that is actually live migration safe, which is kind of neat. Okay, so much for RBD. Whoops. What happened? Hey. There we go. And RESTful storage. RESTful storage is really kind of cool. What that does is we have any number of clients that are anywhere on the web, and they understand nothing but HTTP or HTTPS, and now they want to access the object store through a RESTful gateway. So something that speaks HTTP and produces some JSON containing data from the Ceph objects. And we have that in Ceph. So we have RESTful HTTP and HTTPS access to the object store. And Ceph does that through a FastCGI application named Rados Gateway. And Rados Gateway itself uses the C++ API for Rados, called librados.pp, just in case you're interested. And Rados Gateway runs essentially in any web server that supports the FastCGI interface. So you can run this with Nginx if you choose to. You can run it through Leidy. You can, if you're brave/insane, run it through IIS, which I think supports FastCGI kind of sort of like. But the canonical way of doing this is, interestingly, with Apache and Modfast CGI. For those of you who are Apache geeks, you will probably scream and shout at me that this is not the latest FastCGI implementation that's commonly recommended for use with Apache. That would be modfcgid. But still, it just so happens that the Rados Gateway developers kind of suggest or recommend Modfast CGI for that.
Because of 100 continue support, the FCGI one doesn't handle it properly.
So that was what support?
100 continue.
Oh, okay. So this is apparently about 100 continue HTTP status support, which with FCGID doesn't do too well. All right. So what's nice about Rados Gateway is it did not invent its own wheel in terms of REST APIs that it supports. You can add additional RESTful APIs if you think that's necessary, but the ones that it supports straight out of the box are those for Amazon S3 and OpenStack Swift. The support is not completely feature for feature and bug for bug complete, but the feature disparities are well documented, and there's essentially a list of features that you're getting out of S3 but not out of Rados Gateway, or that you're getting out of Swift but not out of Rados Gateway. Rados Gateway does something very smart, and that is it doesn't put any of its own relevant data or data that is relevant to itself on the Rados Gateway host. Instead, all of that data that it works with, even the stuff that it needs for itself to function, is itself in Rados. So there is no local storage whatsoever. And that means that Rados Gateway completely natively supports load balancing and scale out. If we want to scale out over multiple entry points, then we just add them. We just add one Rados Gateway host and then another and then another and then another, and we can use any sort of load balancing facility that we would like to. One of the more popular ones is, of course, just round-robin DNS. You could theoretically use an IP load balancer, but then that might become a scalability choke point just the same, because now you're redirecting you're directing all your clients through one gateway that then load balances across multiple Rados gateways. Perhaps not the greatest idea, but if you're using DNS load balancing, so round-robin DNS, multiple DNS entries for the same name, then that is just perfectly fine. And we're going to take a look at what that looks like. So we have a Rados Gateway set up on the same hosts, on the same 3 hosts that run the OSDs and the mods. So that's just because it's kind of convenient in this kind of demo setting. Most typical setups would, in production, would run Rados Gateways on separate hosts. As many of them as you like. DreamObjects, which is about 3 petabytes of storage behind Rados Gateway, last I checked used, I think, 4 Rados Gateways, something like that. Just to give you an idea, there's about 100 nodes behind it. So it's a 3-digit number of nodes that's behind it, and there's 4 Rados Gateway hosts that can handle this just very nicely. And by the way, because it's all HTTP and REST and whatnot, you can use whatever caching implementation that you want to use. So if you want to do the same thing that, for example, Wikimedia does for their Swift stuff, which is that they're just strategically placing varnish caches across the globe, and they can run out of a single Swift repository that way, you could do the exact same thing with Rados Gateway, because it's all just HTTP, and you can use the proxying facilities that we all know and love from HTTP. So we're going to start out with some, so what we're doing to interact with this Rados Gateway here is just a completely unmodified Amazon S3 client. Okay? It's using S3 CMD, which is an Amazon S3 client that ships with Debian and Ubuntu and presumably many other distros. And we can just use that to interact with the object store. So what we're first going to do is we're going to see, okay, what kind of buckets do we have on this thing? And we deliberately turned on debugging for this thing just so you can see what is actually coming down on the wire. So in this case, we are connecting to something that actually pretends to be s3.amazonaws.com. We do so with some cute little DNS tricks, so no real trickery here. It's just that on Alice we have a bind, a named that just hosts that zone, and then we go from there. And so we have 3 buckets here, and they are aptly named foobar and baz. So what we're going to do now is we are going to check how we actually interacted with this thing. So there's a utility called Rados Gateway Admin, and that's how we can define our users and permissions and access and things. So in this case, we created a user with the beautiful name of John Doe. He works for example.com, which I hear is a multi-billion-dollar enterprise somewhere in the United States. And what we can define here is just regular old Amazon S3 access keys and secret keys. So for all of you familiar with Amazon S3, that is how you interact with the storage space. And what we've also prepared is we have added credentials for John Doe when he acts as a Swift user. So what we're going to do first is we're going to upload and create an object in there. So we're uploading something to S3, okay? So again, with debugging and la la la. But what we did is we just put something into the foo bucket, okay? And it uses essentially bucket-based host names. So foo.s3.amazonaws.com, and again, there's a little DNS wildcard magic in here. But what we did is we have just created this thing, and if we now go ahead and take a quick look at with our S3 CMD ls, let's see, that went into the foo bucket, and so now there is this thing called foo spam, which I'm talking to using the Amazon S3 API. And now I can do something cool, which is I have created this Amazon S3 bucket, and I've put an object into it, and now I'm going to use Swift addressing that same bucket as a Swift container and retrieving the same object. So there we go, and we just downloaded our object named spam. Okay, and as you can see, what we originally uploaded was the test.txt thing, and it said hello world, which we uploaded using Amazon tools into Rados Gateway and Ceph, and we then retrieved it using a completely unadulterated Swift binary, and did a download request of that object named spam from a container named foo, and lo and behold, it has exactly the same content. So that's kind of neat because we can do these 2 different things, or we can use these 2 completely different APIs with the same object store cluster. And you could do that from Daisy or Eric as well, but that's okay. And then finally, the stuff that you've all been waiting for, because most people tend to perceive Ceph as a distributed file system, which it is, among many other things. Now, in Sage's presentation yesterday, it listed basically all of the components in Ceph, librados, Rados Gateway, RBD, as awesome, and the file system as almost but not quite yet awesome. So this is considered experimental, which is kind of interesting because it is what originally drove the development of Ceph, I think that's fair to say, was to build a Lustre without its shortcomings, right? And there we go, distributed file system on top of Rados, and it's currently considered experimental, although it's been in the mainline kernel since 2.6.32. And that in itself is no surprise because Btrfs has been in the mainline kernel for quite a while and it's still experimental, so that's okay. And you can use it, that is just fine. And there are people that are running this in production, or at least claim to do so on the relevant IRC channels and mailing lists and whatnot. They are typically to be found in academia, which is no surprise because they are also the typical Lustre users. And they're also looking for Lustre without the sock, essentially. And Lustre has a few really painful shortcomings. Number one, it has essential data lookup. It has a metadata server, which is a scalability choke point, and it is a single point of failure, so you have to do a little bit of high availability around that. You can, it also does a few things in the kernel that Ceph does in user space, and a few other things. When I say Lustre without the suck, that of course doesn't mean that Lustre completely sucks. Quite the contrary. It's a very stable HPC file system. It's been in use forever. It's just that it has a few of these shortcomings that people would like to address. And one of those people happened to be Sage and his team at UC Santa Cruz. So, Ceph is the stuff that layers POSIX semantics on top of RADOS. So, Ceph, the file system, introduces things like directories, because in a POSIX file system, the namespace is not flat, it is hierarchical. It introduces attributes, ownership, permission bits, and all the other good things that a POSIX file system needs. And it does so as a very, very, very thin client layer on top of RADOS. Just for the sake of comparison, if you look at single instance storage file systems such as OCFS2 and GFS2, their kernel code is about 35,000 and 68,000 lines of code, respectively. Ceph is 17,000 lines of code, which is like really, really tiny in comparison. And that is because all the others have to take care of lots and lots and lots of things by themselves that in the Ceph file system is just offloaded to RADOS. All the file system metadata itself lives in RADOS objects. And to manage this metadata, we have another type of daemon, the third type of Ceph daemons, called a metadata server, or MDS. And what it does is file system clients, and file system clients only, no RBD clients, nothing that uses librados directly, nothing that uses the Python bindings directly. Only the file system clients actually talk to this metadata server, and the metadata server also caches this metadata for clients to improve performance. It runs entirely in user space, the MDS that is, and only the file system client runs in the kernel. So we only have two components really in Ceph that run in kernel. One is the kernel RBD device, and one is the kernel Ceph file system. There actually is also a Fuse client for Ceph, but that is really only recommended for use in those situations where you are on a system that is not Linux and therefore does not support the file system client but does support Fuse. So that, for example, would be your way of talking to a Ceph file system from, say, FreeBSD, if that's what you want to do. Now, Ceph mounts are writable from any client, so we can mount them from as many clients as we want, and they are, of course, readable and writable from them, and they also play nicely with file locking. All of the file locking, as pretty much anything in Linux as far as file locking is concerned, is advisory. There is no mandatory locking. So applications actually have to ask for locks, and if they don't get it, they have to politely wait. But if they just don't ask for locks, but just barge in, then okay, that's it. But that is how file locking works in Linux in general. And mandatory locking is available as a mount option in just about any file system, and in just about any file system it never really worked. And something that's really cool about Ceph is the Ceph file system is it supports arbitrary directory level snapshots, and what that means is something that we're going to get to in just a moment. It's a really nice way of doing copy on write directory thingies. One thing that is currently unsupported is reflink. Reflink is a means of creating a copy on write duplicate of a single file. That is something that is supported in OCFS2, it is supported in Btrfs where it's called cloning, and that is something that we can't do. So we can't do snapshots of individual files in the Ceph file system, but we can do snapshots of directories, and we can also do snapshots, obviously, of the root directory of the Ceph file system, which means we're snapshotting the entire volume. And Ceph has really spiffy accounting and statistics that it supports through virtually extended attributes. If you're considering you have a, say, 3 petabyte cluster with hundreds of nodes, then finding out how much data is in a specific directory when you're running du is going to be a pretty intensive operation because you're probably going to talk to 100 nodes, which is not fun. So in order to support that better, Ceph has some virtually extended attributes where you can just look that up via an fatr call, which is kind of cool. And this is the final demo, I think, of the entire conference, if you don't count lightning talks. So we are back on Alice again. And the first thing that we can do is crossing our fingers, because yesterday we ran into a memory error problem when we did this. So now we can mount this thing, and it says cannot allocate memory. Yay! Smoke and mirrors. But luckily, we found out how we fix this, and that is we are now going to reboot this thing, which you please do from that. There we go. And it should come back up, and then when it comes back up, and la la la, you know the drill, because we did this yesterday. So here is why the file system is experimental. No, we have several issues here. The Ceph file system development happens completely upstream, and it is actually sort of detached that way from the main Ceph code base because everything just happens in the kernel, and we have a relatively old kernel here, which is a 3.2.0, which, you know, if you're a file system developer, is old. For us mere mortals, it's pretty damn new, but oh well. So, we're going to wait for this thing to come back up.
No, it's back up now.
What was that?
It's back up now.
Ha, that is beautiful. So we just showed you that we can reboot really, really fast. And it has actually mounted. And now we're going to look in what's in there. In the /mnt directory. So that's there. And we just put a Ceph source tree in there. Okay? So there's some Ceph code in there.
It's going faster here.
Yeah, okay. And we're going to do a few things if we just change back into the root directory and do the O4 CephFS thingy. There we go. So for example, we can do the Ceph attributes thing. So what is that? We do a simple fatr call, and it tells us how many files are in this entire volume. Okay, all of them. And how many bytes are in there, and what is the most recent C time in the entire tree, and so forth. So that's really cool, and beats the hell out of doing du or find or whatever over hundreds of nodes and petabytes of data. So that's really kind of a cool feature. We can also interrogate the file system itself about the underlying RADOS properties of things that we do. So in this case, we're just doing a show location of the /mnt directory node, and it tells us exactly what's that RADOS object name and what is its size and where it's at and which OSD is it stored at. And we can also do spiffy things about the file layout. So it will tell us, okay, how many stripes do we have for this particular file, and so forth and so on. So that's really kind of neat. And what is our final thing? Oh, that's right. Yeah, of course, snapshots. So what we also want to do is create a snapshot. And now this is really kind of interesting. Hang on a second.
Sorry.
So what we're doing in order to create a snapshot, there is a in every directory we have this fancy little subdirectory called .snap. And if we create, if we just do a makedir in that, we've magically created a snapshot. So what we can do now is we can nuke everything under /mnt, which is going to take a few moments. There we go. What? Yes? Hey? What? What? Do that again. Did that really nuke anything? There we go. Up. Okay, is that gone? Hang on. So let's see. The snapshot is there. Isn't that beautiful? So what we're going to do now is we're going to do rm ceph and boom. And now we're nuking all of this. It's gone.
Some terminal escape or something screwed up.
Yeah, never mind. That's okay. Chuck. We removed all sorts of stuff. And there's interesting stuff in there, like Java things and whatnot. Oh, that is actually in the... There we go. Yeah, well, dstate, and you know the drill, and la la. Come on. Ah, there we go. And, oops, not quite there yet. Let's see. It should be relative. Ah, there we go. That's gone. That's gone. That's gone. Remove. Oh, come on.
Question.
Yeah, question.
What are you embedding a terminal in a presentation with? Is that a
Shell in a box D.
Cool.
Shell in a box D. Yes, thank you.
We've got another one over here while that's deleting.
Is there going to be quota support on this?
Is there going to be quota support? Sage, is there going to be quota support?
Yeah, eventually. So the recursive accounting is going to be the accounting part, and then we just need to add enforcement.
Okay. So I'm gonna go about 2 minutes over time here, just while we're waiting for this thing to happen. Damn it.
There's one more at the back.
There's one more? Source and UDEV and whatnot. Come on. Well, you know, it's like, it's four OSDs running on, I'm sorry, 3 OSDs running on one laptop. It's probably not going to be fast.
Question at the back.
We can probably move into a combination of question time
Yes,
now
yes,
anyway.
yes. Because, right. Yes, questions. Ha! It's gone. No, it's not gone. Never mind. So, question, yes.
So if we're running,
Wait, take the mic.
if we're running RBD and it's all doing all these lovely things for the volume service, for example,
Yeah.
how unstable is it going to make it if we then throw some metadata servers in front of that? Are we able to do that without endangering the rest?
No, not
of the
happening.
things?
Not happening. You can't just magically migrate from RBD to the Ceph file system. It's completely different. Has data in different pools and all sorts of things. So that if you're just using RBD, then you have no need at all for the metadata service and whatnot. But if you then decide that with this beautiful Ceph cluster that I've built and I've run RBD and Rados Gateway on, etc., you now want to add the Ceph file system, you just fire up a few MBSs and you're good to go.
So given it's unstable, is that going to endanger
It's experimental. It's experimental.
Experimental is far better than unstable.
Yeah. At any rate, you totally need to be geeked out now. Because if you're not, you're positively soulless. Before we get to the questions and things, a bit of a thank you thingy here. So thanks goes obviously to Sage and crew for Ceph. If you're wondering, because you had a question there, what are the presentation tools that we've been using? Impress.js and Shell in a Box. Inktank was nice enough to let us use the Ceph logo. All of the artwork is courtesy of Tim.
Yay.
And if you're interested in this talk or reusing it or whatever, all of that is on GitHub. Here are the URLs. All of this is under the CC by SA20 license. So if you would like to reuse any of the material here, please feel free to do so. Actually, is your handwriting font CC by SA?
Yeah, sure.
Now it is.
And thank you, Florian and Tim.
All right.
Applause. We have a couple of minutes for questions, for further questions.
It actually finished. Hang on a second. Let's go see if that actually finished. So now it's empty. See that? And then I go into the snap directory and into snap 0, and it's all. Oops. It's all there. Okay, question. Let's make this quick because we all want to get to the closing and see lightning talks and things. It'd be awesome.
I would like to briefly go back to the node composition question. We discussed...
Briefly going back is not an option for right now. Next question, please. No, sorry. Go ahead.
Okay, we discussed OSD to spindle ratio.
Yes.
How about core to SSD and core to spindle ratio in a Ceph node?
So on average, count about 1 core 1 gigahertz per OSD.
Okay, one down front there, one up there, and over here.
Simple one. When did you do the snapshot? I didn't recall.
When and how did we do the snapshot? So this is what we did. It is where's the O4 SFFS thingy? Oops. And what we're doing is just this, just up here. We're creating a magic directory. We just do a mkdir mnt/snap, and that's the name of the snapshot, and that's it. That's all we need to do to snapshot things.
Just make a directory.
Yeah, you just make a directory, and the directory is kind of magical because the .snap, the .snap doesn't show up anywhere, because if you actually had that, you know, in the listing of the directory, and then you did an rm/whatever, you nuke the snapshot. And the snapshots are actually read-only, so you can't just nuke them that way. And if you want to remove the snapshot, that's an rmdir, and poof, the snapshot is gone. Question?
Will it work for a 20 gig file?
Will it work for 20 gig farm?
File. If I put a file.
Oh, sure.
What are the limits?
The sky.
That's pretty big. All right, that is really all that we've got time for. Can people put their hands again for Tim, Florian, and... Hang on, don't go away that quickly. We have a little gift here for each of you from LCA 2013.
Thank you.
Thank you very much.
Awesome.
Okay, thank you.
Thanks.